Hello and welcome everyone to the Kubex and Lucidity webinar. Autonomous Kubernetes optimization involves both compute and storage resources. Are you doing both? One of the most powerful capabilities in Kubernetes is the ability to autoscale resources to meet demands, scaling resources up during peak periods to ensure performance and down again during lower periods to save money. What we're going to do in today's session is walk you through what end-to-end Kubernetes optimization looks like when you address both layers together. We're going to have some real examples, demoing, and as well as leaving some time at the end for your questions. Our presenters for today are Andrew Hillier from Kubex and Gino Romanelli from Lucidity. And with that, I'm going to pass the mic over to Andrew to get us started.
Okay, thanks Daniela, and thanks everyone for joining us. I'll just dive right in. I'm going to go first, then Gino's going to go, and I'm excited for this webinar today because it's interesting the parallels between our two products. At Kubex, we do resource optimization, mostly on the compute side. GPU side, we do a bit of ephemeral storage, the local storage to the nodes, but Lucidity does exactly what we don't do, which is the broader storage and the persistent volumes in these environments. So we're going to focus on Kubernetes. We also do cloud optimization. Lucidity also does cloud storage optimization. So you never know, we might have a follow-up webinar on that topic, but let's focus on Kubernetes, probably on ECS, and we can talk about other variants as well. So I'm going to start off just from a compute, CPU, memory perspective, the problem we see when we look at a Kubernetes environment. And it's really, there's multiple problems here. There's inefficiency. There are risks. We see a lot of cases where there's both inefficiency and risk at the same time. I have too many nodes running for the work that's being done, but I also have out of memory kills and throttling. And we address all of those things. But one of the simplest ways to see it is at this level by looking at the aggregate resources running in an environment. And this could be an entire company. This is just a set of labs in this case. And we see quite a bit of inefficiency. And we also see a lack of automation in this area. So Kubernetes does support very high automation in certain ways as far as horizontal scaling and node auto scaling. But when it comes to the resource settings, it's not so good. And so what you end up with is a picture like this, where I'm going to start with the orange line. The orange line are the CPU requests on the left and the memory requests in an environment. So that's how much the application teams are asking for. They might be running a container and asking for 2,000 millicores or 10,000 millicores or 100 millicores. But the problem is they usually ask for more than they're using. So the blue line is actually what's actually being used. And you see it's less than half of what's being requested. And there are good reasons to have some buffer there, but often we see that there's too much buffer. So if I look at that orange line and it's far from the blue line, that means I have pods that are too big. I've been asking for too much CPU or memory capacity when I deploy a pod. The gray line is the allocatable resources in the nodes. So that's what the node autoscaler is effectively turning on. So in this case, I'm asking for 500 cores roughly, or just under. I'm using less than half of that. I'm using under 200 cores, but it's running over 750 cores in the Carpenter environments or the machine sets or the scale groups or whatever it's running on, whatever the node autoscaler is using. And so that gray line being above the orange line is telling us that we need some more efficiency in the node autoscaling. We're running too many nodes. The Kubernetes has to run enough capacity to meet the orange line, but it shouldn't have to run much more than that if it's running efficiently. And there's, again, various reasons why that gap might be bigger. But the idea is we want to get that orange line down closer to the blue line by optimizing the pod resources. And then ideally that gray line would automatically come down closer to the orange line, or we might need to give it a nudge by things like bin packing or optimizing the node types. And even in this example right here, you can see, if you're familiar with this, that the memory on the right, the gray line is really high, meaning I've got a ton of memory deployed that's not even being asked for. Maybe I can just change my node type to a compute optimized or general purpose or something that's more higher CPU ratio and save a bunch of money right off the bat. So we can see quite a bit by looking at this. We see a lot of inefficiency. We see that there's probably auto scaling efficiencies to be had. And that's exactly what we focus on. So what we do is we get all the relevant data from the containers, the nodes, the cloud services underneath. So we do cloud services. And so if Kubernetes is running on the cloud, we model all that side of it as well. And we do a deep analysis of it to figure out what the meaningful patterns of activity are in the container usage. So, what you're looking at is it's a 24-hour time of day pattern saying this container usually gets busy around 9 a.m. till about 4 p.m. and it has peaks and has sustained activity. As we understand the pattern of activity of each container and each pod and how they map the namespaces, and also the replication patterns. So maybe it's using HPA and it's scaling up to 200 copies midday and then back down to 50 overnight. We gather and model all of that and analyze that using policies to figure out how to optimize this environment. And it kind of comes out in two levels. One is the container sizing, the vertical scaling of the containers. Maybe I should make some containers bigger, or maybe I should make them smaller, increase the limits, decrease the requests. Maybe they don't have values, I need to give them values. So there's a set of automatable container recommendations that come out of it, and also node recommendations. Maybe I should be running, like I said earlier, on a different node type, a different shape, as some customers say, or a different size, or it should be scaling differently. And also I'll talk about it, GPUs. If you're running AI workloads on GPUs in Kubernetes, then we'll optimize those as well and say, well, maybe you should be time slicing or somehow fractionalizing those GPUs. So it generates a bunch of different recommendations at different levels. Again, going back to those lines on the chart to basically bring the orange line down and bring the gray line down, or up, as the case may be. It goes both up and down, but in most environments, it's net down, which means saving money. All of that is fed to an automation controller. So we have a pretty advanced automation controller that can just make it so. We find this is becoming very popular. People don't want to edit sort of 10,000 containers by hand in an environment, and doing it through a GitOps flow can be challenging. We're finding that just a mutating emission controller, we also do in-place resizing, that just makes it happen automatically. And so we can do kind of closed loop automation to drive these savings. So you basically turn it on and you get some trust in the answers to make sure they're looking good, and you flip on automation and it should just fix the resource situation. Now, we also have an agentic framework built in. So everything up to that point is all deterministic. It's all using math, basically, and can be completely automated. We also have a set of agents that will do more advanced features, like how big do I make the next container I want to run? Or is HPA set up properly? Should I tune the settings of HPA? Or bin packing, carpenter optimization. And these are also designed to be automated, but some of them might require human in the loop because they are AI. So we have a set of agents and frameworks and tools and MCP tools that will do this job. Some of them are deterministic, some of them are AI, and they can use reasoning to give some very advanced answers, but you might want to approve it before it does it. And so we have a combination of deterministic and agentic use cases. The core automation is all deterministic, but it does some very powerful things. And I can pull it up live and talk a bit about those agents in the demo. From the automation perspective, the automation controller is a key piece. We've done a ton of R&D to do this, to make sure it does it correctly and safely. And I want to emphasize safely. You don't want to start turning on automation and messing up your services. So this thing will go and automatically adjust the requests and limits. Like I mentioned, it has a mutating emission controller. It does in-place resizing. It has very extensive policy controls over exactly what it's going to do. Don't touch the limits, just touch the requests. Don't touch these namespaces. And the idea is that you can turn it on, and what you see here on the top left is it increasing a request, a CPU request, but not touching the limit. The purple line is not being touched. And for memory, we're bringing down the request and the limit. And so it will basically make things safer. We'll upsize things to stop at a memory kill, to stop throttling, to make sure you're requesting enough so you don't overstack the nodes. We'll also downsize things that are oversized. And that's, again, in the balance, most of what happens. And usually net comes way down and saves a ton of money. And everybody wants to be safe, but basically you want to tune that to be the right level so that you're not just stranding a ton of resources that you're having to pay for. So it's all policy driven, extensive safety checks, and those include making sure it doesn't mess up HPA. If you do this wrong, then HPA can start doing unbounded scaling. If you start scaling the attribute that HPA is working against, then you can start having crazy scaling swings. So it's very smart. It understands HPA. It won't conflict with HPA. It understands the nodes you're running on. It won't make something bigger than your biggest node and make it unschedulable. It understands when you're going to exhaust quota, so it won't do things that will exhaust quota or violate limit ranges. And it even does dry runs on the containers to restart them to make sure that if we change them, they're going to come back up. And again, that's not needed if you're doing in-place resizing, but it's very safe in the idea being you turn it on and it will just optimize the resources. And what that looks like is, back to these curves, if you look at the orange line, it's a bit easier to see on the right-hand side on the memory. You can see where automation is turned on, and it starts right-sizing, some down, some up, but mostly down until the orange line is closer to the blue line, meaning the requests are more in line with what's actually being used. And depending on how volatile the workloads are, you can get closer or less close to this. It'll get as close as is safe, but you need the headroom to make sure you can meet the peaks and the bursts in the workloads. So get the orange line closer to the blue line, as close as is safely possible, being very, very safe. And you can see on CPU it came down, and now we have less of a buffer to the blue line. And then ultimately what happens is, where you save the money, is the gray line should come down. and so we're running on fewer nodes because we're not requesting as much capacity. Sometimes that will need a nudge. So again, we can do the container optimization, we'll get this orange line down. In this case, you see the gray line didn't come down. And that's because in this particular example, this is a real example, the max pods per node was set too low in the clusters. And so we recommended that be fixed. And when that got fixed, the number of nodes came down, in this case, to half. And this is what good looks like, where you can right size the pods and then right size the nodes, and you're running better. It's safer because all the limits are high enough and there's no resource shortfalls, but we're still running on much less node capacity. So it's like that win-win of safety and efficiency. When we turn on the automation controller, this is what it tends to look like. And again, the goal is to, I like to think in terms of these colors, get the gray line down, get the orange line down, and make it all run much more efficiently and safely. Back to these agents for a second, they do very specialized functions. I won't go through them all, and I probably don't have time to demo them all. But again, they do some pretty important functions. I mentioned earlier, things like HPA. It'll look at all the granular utilization data. Are things hitting their limits? Is there out of memory kills? Is there throttling, the min and the max? Do we need to adjust the settings of this thing? Do we need to scale it differently with a different threshold or on different parameters? So we'll do a deep analysis of the HPA of the metrics and characteristics and optimize that. Optimizing the carpenter node pools or OpenShift machine sets. Bin packing. Bin packing is a very sophisticated agent. It supports 7 different strategies for scheduler strategies and setting the consolidation threshold of the autoscaler, stateful set affinities. It does a bunch of different things. And the idea being that they're very task specific. Again, like I mentioned, some of them are human in the loop, some of them are actually deterministic, and they drive all the node level optimization. And here's a view of the bin packer actually has a dashboard telling us, here's our bin packing opportunity. You should go after that GPU cluster or node group. In this case, there's a high waste level and opportunity to do some bin packing on that to increase the density, in that case, of the AI workloads. Again, these do much more advanced functions. You can create your own. You can use our AI agent to define whatever logic you want in your environment. And you can hit it through your MCP servers as well, so you can tie it into your enterprise frameworks. Just a quick note on GPU optimization. This is what GPUs tend to look like. We see that the amount of GPUs running, the orange line, is way above the actual resource utilization, that blue line. GPU memory tends to be less bad than GPUs, but the idea here is that gap exists and is very expensive. So in this case, by doing things like MIGs or time slicing, you can actually bring those orange lines down. You can run the same amount of AI workload on fewer GPUs. The cost per token goes down. It's the way a lot of people like to think about it. So I can basically get higher yield. I can do the same amount of inference on fewer actual GPUs. And that's done through a pretty advanced optimization analysis. That on the right, what you see is a GPU optimization map that is analyzing an LLM in this case to figure out, it's currently running on an entire A100, and this is telling it you can run on a quarter of an A100. So that's a MIG recommendation. So the way you read this is that all the different GPUs types and even CPUs, they're here on the right, all the available infrastructure that is available and modeled, and up the side is the size, and it's telling us what you're currently running on and what you could be running on. And this, fits on a quarter of an A100. It would actually fit on an eighth of a B200, but that's probably even more expensive than a quarter of an A100. So it's factoring the benchmarks, all the cost data, and it knows how to do MIGs and also time slicing. So it might also be that I can run it on a T4 time slice, might be a recommendation, not necessarily for this one, but for other workloads. It could even be that you can run on a CPU. This one will actually fit on a CPU, but there's a rule firing saying there's a compatibility issue with that. So the idea is GPU optimization, the AI infrastructure can be optimized quite significantly if you start fractionalizing the GPUs. What I'm looking at is a kind of a top level dashboard of a Kubernetes environment. And just to orient everybody, down the left, I'm looking at the dashboard, and I can define new dashboards of what I'm looking at. I can go deeper into containers and nodes and automation, and I can also look at my cloud, ECS, all the different services we support. So I can look at the cloud underneath this Kubernetes environment as well, but we'll just stick to the Kubernetes environment. And here is that I'm looking at all 18 clusters, about 2,100 containers. So it's a set of labs of what I'm looking at here. And like I described in the PowerPoint, we've got significant inefficiency where we've over requested a lot of resources, and we've also over deployed too many node resources at the top of this thing. And so the gray line is way higher than the actual utilization. I can see at a glance here, if I look around, I also have nodes that are saturated. I have nodes that are at their max pods per node. So even with this surplus of capacity, I also have risks happening. Even though net, I have way too much capacity on the floor, I do have nodes that are running out of capacity or are constrained. I have containers that have limits, events, and kills. I have throttling going on. So this is the before state, and I can see all the different optimization options here and I can drill down them. But what I'm going to do is just flip to a cluster that's been optimized. This is one that's been optimized, and I can go in and look at that curve. So let me just refresh this so it cleans that up, that sawtooth there. But what I'm looking at here is, like I described in the PowerPoint, that automation threshold coming down, where when we turn on automation, you can see it bringing down the requests and then the nodes coming down. In this environment now, we can see that there are no saturated nodes, nothing's at its max pods, and we've gotten rid of all the throttling that the memory kills. And so the automation controller is going to upsize and downsize as it needs to make sure that that's all super clean. So this environment's going to work better, and it's going to run on half the infrastructure. And I can see that if I go over to this automation tab and open it, I can actually see the automation events. These is a cluster, this is a namespace, and here's an actual container, the one that I showed in the PowerPoint. It's one of my favorites, where you can see the actual activity of it changing, dynamically changing the requests and limits to safely optimize this environment. So it's done carefully, and it basically happens over time, and you'll converge on the right amount of capacity. Here's a pretty big upsize. This one was quite undersized for CPU request and way oversized for memory. We see it going in all directions. So that's the automation controller safely changing it.
Can I just interrupt here for a question, please?
Sure.
How do you handle apps that spike at start, then level off much lower during typical workload?
Aha. So we have a JVM user in the audience. So the algorithm used, and I probably don't have time to drill into it in detail, but we set the request and limit independently. We can do guaranteed QoS, but typically we do them separately with different algorithms. So the limit will typically be set above the highest peak in the entire history. And for most of our customers, we'll tune it to be 95 days of history. So we want to see at least a quarter. So we're not going to bring the limit below that high watermark we saw, but the request is a function of the sustained activity. And so, because it's very wasteful to size requests to peak. So the short answer is we'll size the limit above any observed spike. We'll size the request, which is really what's driving cost, to something more sane. And you might want to burst above it at startup, but then you'll be settled within it. And you can tune all this through policy. So we can see exactly how you set those things independently. So that comes a lot for JVMs, where they will have a big spike at startup. We want to make sure that the limits are out of the way so they can do what they need to do. We want to make sure the limit's always out of the way for CPU, so garbage collection works properly. And then it settles down, and the request will reflect that. We can do more dynamic sizing. We have an agent, which is where I was going to go next, which will do predictive sizing, a little more advanced functions. If I look at the agents that are available, you can make it more dynamically sized things. So one of the things we're looking at for JVMs, for example, is to let them start up. And then when they go down, then we can in place resize them downward in the request to make them efficient as they throughout the rest of their lifespan. So there's different strategies available here to do that, but that's very important because the main thing is that you don't constrain anything with a limit, but the requests are safe but efficient. And you want to make the whole system work. As long as the nodes have enough capacity for all the spikes, which is that gap from the blue and the orange, we're okay with the JVM coming up or whatever app coming up and using more resources temporarily. As long as it goes back to its steady state, we'll stay safe. I'll just wrap up the next couple of minutes so Gino has enough time. So there's the agents you can see here. I won't have time to go through them, but I can enter an agent context and I can look at it and I can ask it questions. And this one is a question like, for a certain pod, can I do dynamic sizing? It's saying, yep, between 6 p.m. and 8 a.m., you can make it 234 millicores. During business hours, you can make it 1200. I'm not showing the container, but you can ask these questions, some very advanced questions, to do more advanced functions. And more of these, we're adding automation controllers to do it. For example, this one coming soon, it will automate that automatically and implement that predictive scaling plan. So that's the AI agents. That's the main utilization. And the last thing I'll go to quickly is if I click over on GPUs in this environment, there's 15 containers that are AI workloads running on GPUs. And we're recommending for this one, for example, it's an LLM in dev, and we're recommending it's running on a full A100. We're saying it could be on 3/8 of an A100, and it's going to save you a ton of money. And here's the MIG spec right here. So it'll generate MIG specs off for these things. There's a time slicing Kai schedule integration coming very soon for that. And I can also view that visually in this, and I can click around and see, why not a B200? Well, it's actually way more expensive than an A100. So it's a fully interactive AI optimizing, you can use AI to optimize AI. If you look at what I just showed and, just using a graphic from our website, if you have this operating environment, you turn on automation, we will bring down the requests and the provision capacity to be much more efficient and much safer. Now, as it would happen, if you look at Lucidity's website, there's a very, very similar graphic, uncanny in its similarity. We have different shades of gray, but they do something very, very analogous in the storage world. And I'm going to hand it over to Gino to talk about how that works. And again, they dovetail beautifully because we pick up where each other leaves off. So Gino, I'll hand it over to you.
Thanks, Andrew. As Andrew was just mentioning, right, the handoff between Kubex and Lucidity it makes a lot of sense, right? You focus on resource optimization, but the missing piece often ends up being storage optimization, right? So at Lucidity, we look at the state of cloud block storage, right? We have an assessment tool which allows our customers to really understand their utilization. Most of the customers that we talk to, when you ask them, what their utilization is for their storage, they don't know, right? The hyperscalers make it very difficult to really understand your true utilization. So we have an assessment which is lightweight, read-only, which allows us to pull this data and really analyze where the waste is from a storage perspective, right? Some of the data that we've pulled, over 700 assessments, is kind of shown here by industry. So depending on some of the attendees here, the industries that you're representing, you probably can get a good idea of where your storage utilization is. And then similarly, if you're looking at the OS mix between Linux, Windows, or the particular cloud service provider, you'll get a pretty good grasp as to where there is opportunity to optimize. This assessment can be run in a couple of minutes, like I said, to really showcase where the opportunity is to save on the storage front. And the problem that we're solving is, over-provisioned, underutilized storage. So why is that such a challenge? Well, most of the time with the over-provisioned, underutilized disk, there's a bunch of capacity that you're paying for that you're not using. Oftentimes this will happen when you're creating a new cluster and attaching persistent volumes. You want to give it capacity to grow. And a lot of times, whether that capacity is used or not, you're going to end up paying for it. And when you do have to expand, there's a lot of opportunity to auto expand your storage. But when it comes to shrinking, that often requires downtime, significant planning to migrate data, reattach volumes. And so the problem is there's a lot of manual intervention that happens to right size your capacity. So Lucidity takes this opportunity to optimize your capacity on the storage front. So only paying for what you're actually using, reducing that storage waste, continuously expanding or contracting storage capacity such that that is at a healthy level of utilization, right? And so because of that, we're able to really reduce the downtime required to adjust the capacity of your storage. We're able to do this very quickly, and I'll get into all the details here in a bit. But so many people that we talk to, we ask if they've had to manually expand or shrink capacity. And the answer is always yes. And then the second question is, how much of a headache is it? And a lot of times, depending on the organization with change windows, downtime, pre-planning, everything else, sometimes it just doesn't even get done. And so that's where Lucidity comes in to really take away any of that manual effort for right-sizing your capacity. From the Lucidity perspective, we are application agnostic. We work across the three main hyperscalers, AWS, Azure, GCP. Depending on the application, you will see significant cost reduction, sometimes upwards of 70% because of that utilization level that we showed on the industry benchmark before. And not just on the cost savings piece, but as I want to really drill home is the automation, right? And the hours saved from people having to manually manage your storage environment. And we're obviously focusing on Kubernetes today, so we really want to drill into that. As Andrew mentioned, right, the resource management for Kubernetes is a challenge. So there's a lot of compute waste that's out there. Storage, there's no native autoscaler, right? There's always the ability to expand up and have bursts, but what happens when you're no longer using that storage? The manual intervention required there is both risky and slow, right? Taking that downtime to ensure that you have the capacity at a healthy level. So a lot of times people won't even end up doing that. When we look at Kubernetes, the benefits of Lucidity Autoscaler for Kubernetes is you want to optimize that cloud spend, right? You really only want to pay for what you're using. You want to reclaim engineering time. You want your engineers to be working on things that are going to drive, innovation in the organization, not doing a lot of manual, tedious tasks, and ultimately resiliency and uptime. Anything that you bring in the environment, you don't want to have to deal with any unexpected downtime. And so being able to have that confidence that things are going to continue to operate as normal, business as usual, is critical to any solution that you look at. For Kubernetes itself, I mentioned this a couple different times. We focus on persistent volume optimization. There's a lot of ephemeral storage that is used by Kubernetes, but there are quite a few scenarios in which customers will have persistent volumes, right? Whether it's message queues, Elasticsearch, there are different reasons why you would want to have a stateful set within your Kubernetes environment. And this is really where we're focusing on that optimization piece, right? So it's automated dynamically, and I'll show you that here in the platform. You're able to track the PV utilization in our dashboard as well. There's minimal setup required, and you're only going to be paying for what you're using, right? That is the key component that I want to drive away from why Lucidity is such a good fit for the persistent volume optimization. So how does it work? Lucidity deploys a lightweight agent and a CSI driver in your Kubernetes cluster, which will allow us to send storage metadata only. So we're not in the IO path. We're only collecting information that is going to allow us to make intelligent scaling decisions. So things like utilization, IOPS, throughput, and latency. That's going to get sent to our autoscaler, which I'll demo here in a few minutes. That autoscaler is going to crunch that data, use some machine learning, and then ultimately decide if there's enough capacity on that persistent volume. If there is, then do nothing. If there is too little, then let's add capacity. And if there's too much, then let's reduce capacity, right? And it's doing this all in real time within a couple seconds for expansion operations and within a few minutes for shrink operations, because we really want to make sure that the workload is kind of stabilized before reducing that capacity that you may end up needing for your clusters. And all this is done with zero downtime. You can continue to use your applications without worrying about whether it's going to come offline, whether or not you have to take any of that planned downtime to reduce capacity. It's all happening in real time in the back end. The 3 steps are installing the Lucidity agent, installing the CSI driver, and then onboarding your persistent volumes that you want Lucidity to manage. I'm going to show you how easy it is to get set up here. So in the Lucidity dashboard, this is kind of your landing page in terms of where you're able to look at your pre and post Lucidity utilization, right? So when we're running those analysis, when we're working with customers, really understanding where there's that opportunity to optimize their storage. You'll see your savings in terms of how much you've already saved with Lucidity. You'll be able to look at things like how many auto expansion or auto shrink operations has Lucidity done such that that manual intervention is not required. And then you also see, this is kind of looking at our full block storage autoscaler picture. And I'm going to dive into the Kubernetes component here in a second. But you'll see the data that's currently managed from all of your VMs, your EC2s, your K8s environment, and then also where there's additional opportunity to save, right? And the same holds true on our Kubernetes side. So when we come to the Kubernetes tab of the dashboard here, you can see a couple different things. So the same concepts, right? What have we already saved? Where is there potential to save? And what is being managed by Lucidity today? You can see that we're going to pull in all your clusters after integrating that account into the Lucidity dashboard. You can see your managed persistent volumes and your unmanaged persistent volumes. So if I start with our unmanaged persistent volumes, right, I kind of talked about those 3 steps. The first step is installing the agent and the CSI driver. You can do that through Helm chart installation. It's really quick to do that. Once you've gone and deployed the Helm chart configuration, the next step is we have the agent running there, right? So we want to come back and take a look at onboarding those particular persistent volumes where there's opportunity to save. So we can look at this persistent volume here that we have for this namespace, and we can very easily onboard here. This will start a migration to the new persistent volume that Lucidity will intelligently scale up or down. So once you confirm that, Lucidity will then be managing the persistent volume claims for that persistent volume from your Kubernetes cluster to auto expand or shrink capacity as we're looking at IO for that application. The other case, so that's for onboarding an existing PV, and you can also switch persistent volumes, right? So there's two cases in which you would use Lucidity, right? So for new stateful sets, you can update the storage class for Lucidity to be able to start managing that storage from a new deployment, or we can migrate existing persistent volumes to be managed by Lucidity. That's ultimately where you're going to see that cost savings and reduction from the initial savings analysis. But as you look to add to your environment, that's where Lucidity can also help. Now, once that's done, Lucidity is operating. It's managing this all in the background. It's seamless to the end user. And so if we come back to our managed PVs for this particular cluster here, I can drill down and look at the current utilization and the savings for that volume. I can look at the utilization over time. And so it's very similar to Kubex and their graphs in terms of what's provisioned and what's utilized. what you will see here is this lime green line down here is the data that is being written up to this persistent volume. And up top, this dark green line, that's going to be the capacity that is provisioned, right? So you'll see over time, we are dropping down that capacity where it is no longer needed to maintain roughly 75% utilization, because that's the optimal level for both operational and cost savings, such that you have enough of a buffer to continue to write, but you're only paying for what you're using at a higher utilization level, right? And so operationally, what does this look like? In real time, as we're sending that storage metadata back to our autoscaler, we're able to expand or shrink capacity very, very quickly. In this case, within a couple of seconds for expansion operations. You can see our shrink operations typically take a little bit longer. And like I said, that's for the context of having some buffer there to make sure that the application IO is kind of stabilized, it's in a healthy spot before we remove that capacity that you may need in a couple of seconds or a couple of minutes. So all of that is done really, really quickly. It's a couple easy steps. Like I said, all can be done with zero downtime once you deploy Lucidity to your environment. Andrew and I have kind of both gone through a lot very quickly here, given the time that we have. And so if you are interested in getting a deeper dive with Andrew and his team, I encourage you to scan the QR code here to get a demo for your particular use cases. I know there's been some questions in the chat. And then similarly on the Lucidity side, if you're curious about what your storage utilization is, we can get you set up with a free assessment within a couple minutes, and also drill in deeper to our Kubernetes solution in terms of how we're able to optimize your capacity within your Kubernetes environment.
And I'll just chime in here for a second because I think it's interesting. And in our world, we work with HPA and the node autoscaler and try to make sure it's more intelligent and does the right thing by getting better inputs. And in your world, it's fascinating that there is no autoscaler. I think when you said that, it's very profound that there actually is completely missing in your world, and you provide that, which is pretty fundamental. It's super, super cool what you're able to do with that. I'll also mention quickly, because we also have a similar installation process with Helm charts. There's a forwarder and there's an automation controller. You can install one or both to get it up and running. So even that sense, very similar. We have similar web graphics, we have similar installations, we even have similar QR codes, though they look pretty similar. So it's really an interesting partnership here because they really do complement each other.
I appreciate the time everybody spent with us today and hope it was worthwhile, and look forward to hearing from some of you and helping you guys optimize your Kubernetes environments.
Thanks, everyone.